Late April 1945. Kasumigaura Naval Air Technical Arsenal, Ibaraki Prefecture, Japan. The morning sun cast long shadows across the cratered runway as Commander Minoru Genda approached the damaged American fighter that had forced landed in a nearby rice field 3 days earlier. The aircraft sat covered in canvas tarps surrounded by armed guards, its distinctive inverted gull wings unmistakable even under the concealment. Through the gap in the fabric, Genda could see fabric patches covering damaged sections of the wing improvised repairs using materials salvaged from other crashed American aircraft scattered across the Japanese home islands. This was not supposed to be possible. American fighters were not supposed to penetrate this deep into Japanese airspace and survive long enough to make emergency landings. Yet here sat a Vought F4U Corsair, largely intact, its massive Pratt and Whitney radial engine silent but recoverable. The pilot had escaped, presumably, rescued by American submarines that prowled the coastal waters with impunity. But the machine remained, and with it, an opportunity to understand the weapon that had systematically destroyed Japanese air power over the previous 2 years. Genda had commanded fighter forces at Pearl Harbor. He had watched Japanese Zeros dominate the skies over China, the Philippines, and the Dutch East Indies during the war's early months, when Japanese pilots enjoyed every advantage in training, experience, and equipment. He had also watched helplessly as that dominance evaporated after Midway, as American industry transformed the Pacific War from a contest of pilot skill into a brutal calculation of industrial mathematics, where American factories replaced losses faster than Japanese pilots could inflict them. The Corsair represented everything Genda and his fellow commanders had come to fear about American military power, not just technological sophistication, though the fighter possessed that in abundance, not just speed and firepower, though it exceeded Japanese fighters in both categories. The Corsair embodied American industrial capacity made manifest in aluminum and steel, a philosophy of warfare that prioritized overwhelming material advantage over individual martial excellence. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. As Genda circled the captured fighter, he noted details that engineering teams would document over the following weeks. The aircraft measured 33 feet 4 inches from nose to tail, with a wingspan of 41 feet creating a surface area sufficient to generate enormous lift. The empty weight exceeded 8,900 pounds, nearly 3 times heavier than the Zero fighters that Japanese factories struggled to produce in adequate numbers. Fully loaded with fuel, ammunition, and external stores, the Corsair could weigh 14,000 pounds, yet still achieve speeds that no Japanese fighter could match at any altitude. The inverted gull wing design, initially puzzling to Japanese engineers unfamiliar with such radical departures from conventional aircraft design, served multiple practical purposes that became apparent upon closer examination. The distinctive bend in each wing at the fuselage junction raised the engine high enough to provide clearance for the enormous 13-foot 4-inch diameter propeller without requiring impossibly long landing gear struts. Shorter landing gear meant stronger gear, critical for the violent deceleration of carrier landings where lesser aircraft would collapse on impact. The gull wing also positioned the main wing sections horizontally, optimizing aerodynamic efficiency for high-speed flight, while the angled inboard sections minimized frontal area and drag. Everything about the Corsair's design prioritized carrier operations and high-speed performance, over the maneuverability that Japanese fighter doctrine had emphasized since the early 1930s. Japanese fighters featured lightweight construction, small fuel loads, minimal armor protection, and light armament, all calculated sacrifices to achieve superior turning performance and climb rate in dogfights, where pilot skill could overcome numerical disadvantage. The Corsair rejected that entire philosophy. American designers had built a machine that could absorb punishment, maintain formation integrity despite battle damage, and destroy enemies through superior speed and firepower before opponents could exploit maneuverability advantages. The first comprehensive encounter between Corsairs and Japanese fighters had occurred over Guadalcanal beginning in February 1943. 12 Corsairs of Marine Fighting Squadron 124, commanded by Major William Guise, arrived at Henderson Field on February 12. Their first combat engagement came 2 days later when Corsairs escorted consolidated B-24 Liberators on a raid against Japanese positions at Kahili. Japanese Zero fighters intercepted the formation with aggressive determination, shooting down 4 P-38s, 2 P-40 Warhawks, 2 Corsairs, and 2 Liberators, while losing perhaps 4 aircraft themselves. The Americans would later refer to this engagement as the St. Valentine's Day Massacre, acknowledging the tactical defeat. But Japanese intelligence officers studying the engagement reports noticed disturbing trends that would become more pronounced in subsequent encounters. The Corsairs had sustained battle damage that would have destroyed Zero fighters, yet continued flying and fighting. American pilots demonstrated consistent discipline, refusing to engage in low-speed turning contests where Zero pilots held advantages. When Corsairs attacked, they dove from altitude, fired concentrated bursts from 650 caliber machine guns that could shred aircraft at ranges exceeding 600 yards, then used superior speed to disengage before Japanese pilots could respond effectively. Within weeks, Marine Corps pilots learned to exploit every advantage the Corsair provided. Second Lieutenant Kenneth Walsh of VMF 124 would become the first Corsair ace by May 1943, accumulating victories through systematic application of energy fighting tactics that leveraged the Corsair's strengths while avoiding its weaknesses. Walsh later explained the tactical revelation that transformed Corsair operations. Altitude dictated the terms of every engagement. Whoever held the height advantage controlled when to attack, where to attack, and when to disengage. Zero pilots who had dominated early war encounters through superior maneuverability found themselves unable to force combat when Corsair pilots maintained altitude and speed discipline. The mathematics were brutal and undeniable. The Corsair F4U-1 model entering service in 1943 achieved maximum speeds exceeding 400 miles per hour at altitude, powered by the Pratt and Whitney R2800 double wasp 18-cylinder radial engine producing 2,000 horsepower. The 0A6M5 variant, the most advanced model Japan deployed in significant numbers during 1943, achieved maximum speeds of approximately 330 miles per hour using the Nakajima Sakai engine, producing 1,130 horsepower. A 70-mile-per-hour speed differential meant Corsair pilots could engage or disengage at will. Zero pilots could only fight when Corsairs chose to fight. Climb performance told an equally discouraging story for Japanese tactical planners. The Corsair achieved initial climb rates exceeding 2,900 feet per minute, allowing pilots to reach 20,000 feet in roughly 7 minutes. The Zero climbed faster initially at low altitude, exceeding 3,000 feet per minute, but Japanese pilots required 25 minutes to reach 30,000 feet where oxygen equipment became critical. American pilots routinely operated at altitudes where Japanese pilots struggled to maintain consciousness, attacking from positions where Japanese defensive doctrine provided no adequate response. The armament disparity proved even more devastating in practical combat application. The Corsair mounted 6 Browning M250 caliber heavy machine guns, 3 in each outer wing panel. Each gun fired at approximately 750 rounds per minute, creating a combined rate of fire exceeding 4,500 rounds per minute across all 6 guns. With 75 rounds per second filling the target zone, even brief firing opportunities proved lethal. The ammunition load carried 2,350 rounds distributed across all positions, providing approximately 30 seconds of continuous fire, far more than needed for multiple engagement opportunities during typical missions. The 50 caliber Browning fired cartridges delivering kinetic energy approximately 3 times greater than the 7.7 mm Type 97 machine guns that Japanese fighters mounted for secondary armament. Each 50 caliber round could penetrate armor plate, destroy engines, shatter canopies, and kill pilots from ranges where Japanese machine guns proved ineffective. The rounds also created massive hydrostatic shock when striking fuel tanks or human tissue, causing catastrophic damage from near misses that would have proven harmless from smaller caliber weapons. Zero fighters mounted two 20mm Type 99 cannons in the wings as primary armament, weapons theoretically superior to 50 caliber machine guns in destructive potential per hit. Each cannon fired explosive shells weighing approximately 4.5 ounces compared to roughly 1.5 ounces for 50 caliber bullets. A direct hit from a 20mm shell could destroy critical aircraft components or kill crew members instantly. But the cannons fired at only 490 rounds per minute combined, roughly 1/10 the volume of fire that Corsair guns delivered. The ammunition load provided only 120 rounds total, giving Japanese pilots perhaps 15 seconds of firing time before exhausting cannon ammunition. The tactical implications became obvious to any pilot who survived multiple encounters. Corsair pilots could spray defensive fire during disengagement maneuvers, forcing pursuing Zero pilots to evade rather than close to effective cannon range. Zero pilots who exhausted cannon ammunition in unsuccessful attacks faced opponents armed with thousands of rounds of 50 caliber ammunition who could engage repeatedly throughout extended missions. Japanese pilots needed precision to achieve kills with limited ammunition. American pilots could rely on volume of fire, knowing that even a few hits from dozens of rounds fired would likely prove fatal. But the most significant advantage the Corsair provided came from rugged construction and damage tolerance that reflected fundamentally different design philosophies between American and Japanese aviation. Japanese fighters emphasized lightweight construction using minimal structural materials to maximize performance through reduced weight. Zero fighters featured aluminum skin as thin as 0.5 mm in non-critical areas, unarmored fuel tanks to save weight, no cockpit armor to protect pilots, and minimal structural redundancy, where single component failures could prove catastrophic. The design philosophy accepted vulnerability as the price of performance, assuming skilled pilots would avoid situations where enemies could exploit that vulnerability. American designers rejected those compromises entirely. The Corsair employed heavy-gauge aluminum alloy frames and stressed skin construction, distributing loads across the entire airframe. Multiple redundant systems meant single failures rarely threatened missions. Self-sealing fuel tanks prevented fires from small-caliber hits through rubber lining that swelled when punctured, closing holes before fuel could leak. Armor plate protected the pilot's position, engine, and critical systems with particular attention to preventing catastrophic failures from battle damage. The pilot sat behind a thick slab of armor plate capable of stopping 20mm cannon shells, ensuring survival even when struck during head-on passes. The cumulative effect of these design features meant Corsairs absorbed punishment that would destroy Japanese fighters while continuing to fly and fight. American after-action reports documented Corsairs returning to base with dozens of bullet holes, damaged control surfaces, disabled weapons, and destroyed instruments yet still flying under control. Some returned with engines barely functioning after, taking multiple 20mm hits that should have caused immediate catastrophic failure. Pilots reported incidents where armor plate stopped cannon shells that would have killed them instantly in unprotected aircraft. Japanese pilots encountering Corsairs for the first time during 1943 found their previous tactical doctrines increasingly ineffective against opponents who could absorb battle damage, maintain formation discipline under fire, and deliver devastating return fire from 6 heavy machine guns. The turning contests that allowed skilled Zero pilots to dominate F4F Wildcats and P-40 Warhawks during early war engagements proved suicidal against Corsairs, whose pilots refused to slow down and engaged only from favorable positions. Commander Genda understood these tactical realities from extensive combat reports filed by surviving Zero pilots throughout 1943 and 1944. He had read descriptions from pilots who successfully positioned behind Corsairs, only to watch targets accelerate away before cannons could achieve effective range. He had studied reports from pilots who hit Corsairs with 20mm shells that should have been fatal, yet watched targets continue flying. He had reviewed intelligence assessments, estimating Corsair production exceeded 200 aircraft monthly from multiple factories, while Japanese production of all fighter types barely exceeded 500 aircraft monthly, despite mobilizing every available resource. The implications extended far beyond individual combat encounters or tactical advantages. The Corsair represented a complete system of warfare that American industry could produce faster than Japanese forces could destroy them. Every Corsair shot down over the Pacific would be replaced by 2 more within weeks. Every American pilot killed in combat would be replaced by 5 trained replacements produced through systematic flight training programs operating in safety, beyond Japanese reach. Every bullet expended defending Japanese positions would need to be manufactured in factories that American bombers attacked with increasing frequency and effectiveness. By late 1944, when this particular Corsair was manufactured at Chance Vaught's Connecticut facility, American industry had achieved production rates that seemed impossible to Japanese military planners who understood manufacturing capacity. Vought, Goodyear, and Brewster companies combined to build nearly 600 Corsairs during May 1944 alone, the peak production month. By war's end, total production would exceed 12,571 aircraft built over 10 years of continuous manufacturing. Japanese industry, operating under constant air attack with disrupted supply chains and insufficient raw materials, struggled to produce 5,000 fighters of all types during the entire year of 1944. Even that inadequate production required mobilizing forced labor, operating factories around the clock despite bombing raids, and accepting declining quality control as experienced workers died or became too exhausted to maintain standards. The Zero fighters that Japanese factories delivered in 1944 showed rough workmanship, mismatched panels requiring hand-fitting and improvised repairs using non-standard materials that reflected an industrial base in collapse. Genda stood beside the captured Corsair's cockpit, studying the instrument panel through the damaged canopy. American designers had arranged instruments in standardized positions that remained consistent across different aircraft types, allowing pilots to transition between aircraft more easily. Circuit breakers replaced fuses in the electrical system, providing resettable protection that simplified troubleshooting and maintenance. The throttle quadrant operated with reversed logic compared to Japanese aircraft, with forward motion increasing power rather than decreasing it. These design decisions reflected an industrial philosophy, emphasizing mass production efficiency, standardization for rapid training, and logistical simplification for global operations. Everything about the Corsair contradicted the artisanal approach Japanese industry still employed despite wartime pressures. Where Japanese aircraft required skilled craftsmen to hand-fit complex components through labor-intensive processes, American designers specified standardized modules that semi-skilled workers could install rapidly using jigs, templates, and fixtures. Interchangeable parts meant components manufactured at different factories across America would fit together without custom fitting. Simplified assembly sequences reduced the skill level required for workers, allowing factory managers to employ women, elderly workers, and others previously considered unsuitable for complex aircraft manufacturing. The implications were staggering for Japanese planners who understood industrial capacity. If American factories could produce Corsairs at rates exceeding 500 aircraft monthly, using semi-skilled labor in factories immune from enemy attack, while Japanese factories struggled to produce adequate numbers despite mobilizing every available worker and operating under constant bombardment, how could Japan possibly win a war of industrial attrition? Japanese technical intelligence teams would spend weeks examining the captured Corsair at Kasumigaura, documenting every system, measuring every component, testing every control surface response. They would marvel at manufacturing quality reflected in precision tolerances that Japanese craftsmen admired. They would analyze stressed skin construction techniques that demonstrated sophisticated understanding of load distribution. They would study self-sealing fuel tank design that Japan had never implemented comprehensively despite understanding the technology. They would photograph electrical systems, hydraulic controls, oxygen distribution, and intercom systems that revealed American approaches to aircraft systems integration. But all that technical knowledge couldn't change the fundamental reality that Genda recognized standing beside this captured fighter. Understanding your enemy's advantages doesn't eliminate them or create counters when the resources don't exist. The Japanese aviation industry could reverse engineer every innovative feature, could copy every advanced system, and could replicate every manufacturing technique and still couldn't produce Corsairs in quantities needed to challenge American air superiority because the industrial foundation required for such production had never existed in Japan and couldn't be built while fighting a losing war against opponents who possessed overwhelming material advantages. The engineers who would examine this Corsair already knew the technical specifications from studying damaged aircraft recovered from combat zones and from intelligence reports compiled through prisoner interrogations. They knew the Pratt and Whitney engine produced 2,000 horsepower. They knew the maximum speed exceeded 400 miles per hour. They knew the armament consisted of 6 50-caliber machine guns with over 2,000 rounds of ammunition. They knew the combat radius exceeded 285 nautical miles with external fuel tanks. They knew the service ceiling exceeded 41,000 feet. They knew the empty weight exceeded 8,900 pounds. But knowing these specifications was different from understanding what they meant in the broader context of industrial warfare. Each number represented American capabilities that Japanese industry couldn't match. The 2,000 horsepower engine reflected a sophisticated understanding of metallurgy, precision manufacturing, and materials science that Japanese industry had never mastered. The long range reflected fuel capacity and consumption efficiency that Japanese designers couldn't achieve without accepting weight penalties that destroyed performance. The heavy armament reflected confidence in structural strength that allowed mounting 6 heavy weapons without compromising airframe integrity. The high service ceiling reflected supercharger technology and oxygen systems that Japanese pilots couldn't rely on at extreme altitudes. The sound reached Japanese positions before the aircraft became visible. A distinctive high-pitched whistle created by wind rushing through the engine cooling vents and oil cooler intakes in the wing roots announced the Corsair's approach during high-speed dives. Japanese soldiers defending positions throughout the Solomon Islands came to recognize that sound with visceral dread. When you heard the whistle, death followed seconds later in the form of 6 50-caliber machine guns or 1,000-pound bombs delivered with devastating accuracy. Japanese ground forces coined the nickname that would define the Corsair in Pacific warfare. They called it the Whistling Death, a phrase that captured both the acoustic signature and the lethal consequences of encountering the American fighter. The name spread through Japanese military communications, appearing in intelligence reports, unit diaries, and pilot briefings. By late 1943, every Japanese serviceman in the South Pacific understood what the whistling sound meant and reacted accordingly. But understanding the threat and countering it effectively were entirely different matters. Japanese pilots facing Corsairs in aerial combat learned quickly that traditional zero tactics proved suicidal against opponents who controlled altitude, speed, and firepower advantages simultaneously. The most celebrated Japanese ace to survive the war would later acknowledge the fundamental shift in air combat that the Corsair represented. Saburo Sakai, who accumulated 28 confirmed victories according to official Japanese records and survived over 200 dogfights from China to Iwo Jima, flew his first combat missions when Japanese Zeros dominated Pacific skies. In his autobiography, Samurai, published in 1957 with American journalist Fred Saito and aviation writer Martin Kadin, Sakai described watching Japanese air superiority evaporate as American industry delivered progressively more capable fighters in overwhelming numbers. He acknowledged that the Corsair became the most feared Allied aircraft among Japanese pilots who understood its capabilities. The transformation from Japanese dominance to American superiority occurred with remarkable speed after Midway. The battle in June 1942 destroyed 4 Japanese fleet carriers and eliminated veteran pilots who couldn't be replaced quickly enough through Japan's limited training programs. The Japanese Naval Air Force trained only 26 new fighter pilots total during 1937, the year Sakai graduated first in his class. That inadequate production reflected a training philosophy emphasizing quality over quantity, assuming that superbly trained elite pilots flying superior aircraft would dominate numerically superior but less skilled opponents. The Americans pursued the opposite philosophy. Mass production of pilots through standardized training programs operating in safety beyond Japanese reach meant thousands of new aviators graduated annually. American doctrine rotated experienced pilots out of combat after 25 missions initially, later increased to 35 as loss rates declined. Those survivors returned to training commands, where they taught new generations of pilots using lessons purchased with blood over Pacific combat zones. The system created institutional learning that preserved and transmitted combat experience across pilot generations. Japanese pilots, by contrast, flew until killed, captured, or physically unable to continue from wounds or exhaustion. No systematic rotation policy existed. Every pilot capable of flying combat missions stayed on the line, leading to declining average experience levels as veteran pilots died faster than training programs could produce skilled replacements. By late 1943, many Japanese pilots entered combat with minimal flying hours and inadequate preparation for the tactical realities they would face against aircraft like the Corsair. The first major encounter between Corsairs and concentrated Japanese forces occurred over Rabaul, the massive Japanese base complex in New Britain that supported operations throughout the Solomon Islands. Japanese forces had developed Rabaul into the most formidable fortress in the South Pacific, with multiple airfields surrounded by hundreds of anti-aircraft guns and defended by some of Japan's most experienced fighter units. By late 1943, however, American strategy shifted toward isolating and neutralizing Rabaul through sustained air attacks rather than attempting costly amphibious assault. Marine Corsair squadrons led this campaign. Major Gregory Boyington's VMF-214, nicknamed the Black Sheep Squadron due to comprising replacement pilots who had arrived in the South Pacific without permanent unit assignments, achieved remarkable success during operations over Rabaul between September 1943 and January 1944. The squadron destroyed over 200 Japanese aircraft during 84 days of intense combat, with Boyington personally credited with 22 victories during this period, to add to 6 he had scored earlier while flying with the American Volunteer Group in China. Boyington's success reflected systematic application of tactics that exploited every Corsair advantage while avoiding situations where Zero pilots could leverage their aircraft's superior low-speed maneuverability. Altitude was paramount. Whoever held height advantage dictated engagement, terms, choosing when to attack, where to attack, and when to disengage. Zero pilots who had dominated early war encounters through superior turning performance found themselves unable to force combat when Corsair pilots maintained altitude and speed discipline. The tactical doctrine was simple, but required iron discipline to execute consistently. Corsair pilots climbed to altitude before entering combat zones, typically operating at 20,000 to 25,000 feet, where the fighter performed optimally. When Japanese fighters appeared below, Americans dove from altitude, accelerating to speeds exceeding 400 miles per hour. They selected targets, fired concentrated bursts from 650 caliber machine guns, then used superior speed to zoom climb back to altitude before Japanese pilots could respond effectively. If pursued, Corsair pilots simply accelerated away, using their 70-mile-per-hour speed advantage to open distance until threats disengaged. Japanese pilots attempting to pursue found themselves helpless. Zero fighters at full throttle couldn't catch Corsairs in level flight. Attempting to climb after diving, Corsairs proved equally futile as the American fighters outclimbed Zeros at medium and high altitudes. The only option that offered any chance of success involved positioning above Corsair formations before engagement, but American radar controllers and combat air patrol procedures made achieving altitude advantage increasingly difficult as the war progressed. Lieutenant Kenneth Walsh of VMF-124 became the first Corsair ace on May 13, 1943, shooting down his 4th, 5th, and 6th Zero fighters during a single mission over the Russell Islands. Walsh, who had earned his pilot wings in 1937 as a Marine private, demonstrated absolute fearlessness in aerial combat throughout his career. On August 30, 1943, he single-handedly attacked a formation of 50 Zero fighters intercepting Army Air Force's B-24 Liberators over Bougainville. In the wild melee that ensued, Walsh shot down 4 enemy fighters before being forced to crash at sea after sustaining battle damage. He survived, received the Medal of Honor, and returned to combat operations, eventually claiming 21 confirmed victories. Lieutenant Robert Hansen of VMF 215 achieved even more remarkable success during his brief combat career. Starting service with the squadron on October 6, 1943, he scored his first victory on November 1. By the beginning of large-scale battles over Rabaul, Hansen had accumulated 5 victories. In the following 17 days, he brought his combat score to 25 aircraft, making him the highest-scoring Corsair ace of the war. On February 3, 1944, while attacking Japanese anti-aircraft positions, his aircraft was damaged and fell into the sea. Hansen's meteoric rise from novice top ace in less than 4 months demonstrated both the Corsair's effectiveness in skilled hands and the increasingly desperate situation facing Japanese defenders, who couldn't replace losses fast enough to maintain effective resistance. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Boyington's final mission on January 3, 1944, illustrated both the effectiveness of Corsair tactics and the continuing dangers facing even the most skilled pilots. Leading a raid on Rabaul, Boyington became separated from his squadron by bad weather. He and his wingman encountered a large formation of Zero fighters and engaged despite being heavily outnumbered. Boyington shot down 2 more enemy aircraft, bringing his total to 28 confirmed victories, before being shot down himself while defending his wingman from attacking fighters. Although injured, he successfully executed. A water landing, was strafed by Japanese fighters still overhead, and was eventually rescued by a Japanese submarine. He spent the remainder of the war as a prisoner, receiving the Medal of Honor after liberation in August 1945. The combat statistics compiled from these operations told a story of overwhelming American tactical success, despite fierce Japanese resistance. By February 1944, when Japanese forces withdrew surviving air units from Rabaul after acknowledging defeat in the campaign, Marine Corsair squadrons had established air superiority through systematic destruction of Japanese air power. The 11-to-1 kill ratio that Corsair pilots eventually achieved represented the lowest loss rate of any fighter in the Pacific War, though this figure reflected operational circumstances as much as aircraft capability. The Corsair faced intense air-to-air combat primarily during the Solomons and Rabaul campaigns, as well as at Leyte and during kamikaze interception. As operations shifted northward and the Corsair's mission transitioned increasingly toward ground attack, it saw less exposure to enemy aircraft, while other American fighters continued engaging Japanese forces in air combat. Against the best Japanese opponents during the period when both sides fielded experienced pilots flying at full strength, the Corsair claimed a 12-to-1 kill ratio against the Zero and a 6-to-1 ratio against more advanced Japanese fighters, including the Nakajima Ki-84 Frank, the Kawanishi N1KJ George, and the Mitsubishi J2M Jack. These numbers reflected systematic American advantages in pilot training, tactical doctrine, and aircraft performance that Japanese forces couldn't overcome through individual skill or desperate courage. The captured Corsair at Kasumigaura represented an opportunity for Japanese technical intelligence to understand their opponent through systematic examination rather than fragmentary combat. Reports. Engineers who examined the aircraft during late April and May 1945 documented every system, measured every component, and tested every control surface response with the same methodical thoroughness that German engineers had applied to captured B-17 bombers at Rechlin. But the knowledge gained provided no consolation and suggested no solutions to the fundamental problems facing Japanese air forces. The Pratt and Whitney R-2800 double wasp engine that powered the Corsair represented sophisticated metallurgy and precision manufacturing that Japanese industry couldn't match. The 18-cylinder radial engine produced 2,000 horsepower in standard configuration, with later variants achieving 2,250 horsepower through water injection systems for emergency power boosts. Japanese engine development had stagnated after early war successes, unable to produce more powerful radial engines without accepting catastrophic reliability problems that grounded aircraft faster than combat losses. The Nakajima Sakae engine powering Zero fighters produced 1130 horsepower maximum, less than 60% of the Corsair's output. Attempts to develop more powerful engines for Japanese fighters encountered insurmountable materials science and manufacturing problems. The Mitsubishi Kasei engine, intended for advanced fighter variants, suffered chronic overheating and mechanical failures. The Nakajima Homare engine proved even worse, with such terrible reliability that pilots called it the troublemaker and preferred flying older aircraft with proven Sakai engines despite accepting performance disadvantages. American engines ran reliably for hundreds of hours between overhauls. Japanese engines required constant maintenance and frequent replacement of worn components. The disparity reflected differences in industrial capacity, materials quality, and manufacturing precision that widened throughout. The war as American industry operated in safety, while Japanese factories endured constant air attacks that destroyed tooling, killed skilled workers, and disrupted supply chains. The self-sealing fuel tanks that Japanese engineers examined in the captured Corsair represented technology that Japan understood but had never implemented comprehensively. American fighters featured rubber-lined tanks that swelled when punctured, closing holes before fuel could leak and ignite. Japanese fighters retained unprotected tanks to save weight, accepting catastrophic vulnerability to incendiary ammunition. Zero pilots knew that a single incendiary round striking a fuel tank would likely cause immediate fire and explosion. Corsair pilots understood their tanks could absorb multiple hits and continue functioning, providing psychological confidence that affected tactical decision-making in combat. The armor plate protecting the Corsair pilot represented similar philosophical differences. A thick slab of hardened steel behind the pilot's seat could stop 20mm cannon shells, ensuring survival even when struck during head-on passes. Additional armor protected the engine and critical systems. The cumulative weight of this protection exceeded 400 pounds, but American designers accepted that penalty to improve survivability. Japanese designers eliminated armor entirely to maximize performance through weight reduction, assuming skilled pilots would avoid situations where protection proved necessary. These design philosophies reflected different strategic situations and industrial capabilities. Japan, as an island nation lacking natural resources and dependent on imported raw materials, couldn't afford the steel, aluminum, and rubber needed for comprehensive armor and self-sealing tanks across its entire fighter force. Even if materials had been available, Japanese industry lacked the manufacturing capacity to produce them in required quantities while simultaneously building airframes, engines, and weapons systems. American industry faced no such constraints. Abundant domestic resources, safe factories immune from enemy attack, and manufacturing capacity exceeding all Axis nations combined meant American designers could specify protective features that Japanese engineers couldn't contemplate. The ammunition load carried by the captured Corsair's 650 caliber machine guns totaled 2,350 rounds distributed across all positions. That provided approximately 30 seconds of continuous fire, far more than needed for multiple engagement opportunities during typical missions. Zero fighters carried only 120 rounds total for their two 20mm cannons, providing perhaps 15 seconds of firing time before exhausting primary armament. Japanese pilots needed precision shooting to achieve kills with limited ammunition. American pilots could rely on volume of fire, knowing that even a few hits from dozens of rounds fired would likely prove fatal. The industrial mathematics underlying these disparities became undeniable when Japanese engineers examined production data from American factories. By 1945, when this particular Corsair was manufactured at Chance Vaught's Connecticut facility, American industry had achieved production rates that seemed impossible to Japanese planners. Vought, Goodyear, and Brewster companies combined to produce nearly 600 Corsairs during May 1944 alone, the peak production month. Total production would eventually exceed 12,571 aircraft, built between 1940 and 1952, when manufacturing finally ceased. Vought built 8,941 Corsairs across all variants from its Connecticut facility. Goodyear contributed 4,014 aircraft designated FG-1 from plants in Ohio. Brewster produced 735 fighters, designated F3A-1 from facilities in New York, before quality problems forced the Navy to cancel further orders. Even after eliminating Brewster's troubled production, over 13,000 Corsairs entered service with American, British, New Zealand, and French forces operating across the Pacific, Atlantic, Mediterranean, and eventually Korea. Japanese industry operating under constant air attack, with disrupted supply chains and insufficient raw materials, struggled to produce 20,000 fighters of all types during the entire war. That total included Zeros, Army fighters, interceptors, and experimental types, representing Japan's complete fighter production from 1941 through 1945. The United States produced more Corsairs alone than Japan produced fighters total, and the Corsair represented only one of multiple American fighter types manufactured simultaneously in overwhelming quantities. The production disparity extended beyond airframes to every component of modern warfare. American factories produced over 300,000 aircraft of all types during the war years, including fighters, bombers, transports, and trainers. They built 98,000 tanks and self-propelled guns. They manufactured 41 billion rounds of ammunition. They constructed thousands of ships ranging from escort carriers to battleships. And they accomplished this industrial miracle while simultaneously producing consumer goods for civilian populations who never experienced rationing on the scale that Japanese, German, or British civilians endured. Commander Genda understood these realities from years of studying American industrial capacity and observing its impact on Pacific combat operations. The captured Corsair sitting before him at Kasumigaura represented not just technological sophistication or tactical advantages. It embodied American industrial civilization's capacity for sustained production that Japanese forces couldn't match through any realistic means. Every technical feature that impressed Japanese engineers reflected industrial capabilities and resource allocations that Japan lacked and couldn't develop while fighting a losing war against opponents who possessed overwhelming material advantages. The examination of the captured Corsair proceeded with scientific rigor throughout May 1945. Engineers photographed every system from multiple angles. They measured skin thickness, analyzed alloy composition, tested rivet patterns and joining techniques. They removed panels to study structural design, marveling at the stressed skin construction that gave the fighter its legendary toughness. They documented electrical systems, hydraulic controls, oxygen distribution, fuel management, and engine synchronization. They studied the inverted gull wing design, understanding how it provided propeller clearance while maintaining aerodynamic efficiency. But all this technical knowledge couldn't change strategic outcomes. Understanding your enemy's advantages doesn't eliminate them or create effective counters when necessary resources don't exist. Japanese engineers could reverse engineer every innovative feature, copy every advanced system, replicate every manufacturing technique, and still couldn't produce Corsairs in quantities needed to challenge American air superiority. The industrial foundation required for such production had never existed in Japan and couldn't be built while fighting a desperate defensive war against enemies who controlled the seas, dominated the skies, and attacked Japanese cities with increasing frequency and effectiveness. By May 1945, when engineers examined the captured Corsair, Japan's strategic situation had deteriorated beyond any hope of recovery. American forces controlled Okinawa, placing B-29 superfortress bombers within easy range of Japan's home islands. Incendiary raids had destroyed large sections of Tokyo, Osaka, Nagoya, and dozens of smaller cities. The naval blockade prevented importation of food, fuel, and raw materials needed to sustain military operations or civilian populations. Japanese industry, what remained of it after months of strategic bombing, operated at a fraction of wartime peak capacity. The Corsairs that had dominated Pacific skies since 1943 now operated from captured Japanese bases, attacking remaining defensive positions with impunity. American pilots flew multiple missions daily against targets throughout Japan, facing minimal opposition from Japanese fighters that lacked fuel, ammunition, and replacement pilots. The final desperate resort to kamikaze attacks acknowledged Japan's inability to achieve air superiority through conventional means. Converting fighters into suicide weapons represented an admission that Japanese pilots couldn't defeat American aircraft through skill and courage alone. The accident rate for Corsairs during the war years revealed the aircraft's demanding flight characteristics, despite its combat effectiveness. Only 189 Corsairs were lost in air-to-air combat throughout the Pacific War, reflecting the dominant kill ratio achieved by American pilots. 349 fell to ground fire during attack missions against heavily defended targets, but 692 were lost in non-operational accidents, and 230 were lost in operational accidents during combat missions. The combined accident total exceeded combat losses significantly, demonstrating that the Corsair remained a challenging aircraft to fly safely, even for experienced pilots. The accident statistics reflected design compromises that made the Corsair an exceptional combat aircraft, while creating difficulties for carrier operations and training environments. The long nose that housed the powerful engine obstructed forward visibility during landing approaches. The enormous torque from the double Wasp engine made the aircraft difficult to control during slow-speed maneuvering. The wing's tendency toward asymmetric stall at low speeds created dangerous handling characteristics during the critical final approach phase of carrier landings. One Marine training base, MCAS Mojave, recorded at least 144 Corsair training accidents, earning the fighter the unfortunate nickname Ensign Eliminator among Navy pilots who considered it unsuitable for carrier duty. The British Royal Navy Fleet Air Arm solved many carrier landing problems through innovative procedures that American pilots later adopted. Instead of the standard downwind-crosswind final approach that required maintaining visual contact with the carrier deck through the final turn, British pilots executed a continuous curving approach that kept the landing signals officer visible until the last second before touchdown. They wired shut the cowl flaps across the top of the engine compartment to divert oil and hydraulic fluid around the fuselage sides, rather than allowing it to smear the windshield. These and numerous other modifications transformed the Corsair from an aircraft deemed unsuitable for carrier operations into an effective carrier fighter that served extensively with British, American, and French naval forces. The United States Navy finally accepted the Corsair for shipboard operations in April 1944 after implementing improvements, including a longer oleo strut that eliminated the tendency to bounce during hard landings. The first American carrier-based Corsair unit, Marine Squadron VMF-124, joined the carrier Essex in December 1944, proving that the fighter could operate effectively from carriers despite its challenging handling characteristics. By war's end, Corsairs flew 64,051 operational sorties for Marines and Navy through the conflict, with only 9,581 sorties flown from carrier decks. The remaining 85% of missions launched from land bases, where the Corsair's demanding takeoff and landing characteristics posed fewer risks. The captured Corsair at Kasumigaura would never fly again. Fuel shortages prevented test flights, even if Japanese engineers had wanted to evaluate its performance characteristics through practical demonstration. The examination remained theoretical, limited to static testing and documentation. In early August 1945, as American forces prepared for the planned invasion of Japan's home islands, events overtook the Technical Intelligence Program. The atomic bombings of Hiroshima on August 6th and Nagasaki on August 9th, combined with Soviet entry into the war on August 8th, forced Japan's surrender on August 15th. The captured Corsair survived the war, eventually falling into American hands during the occupation. Similar captured aircraft underwent thorough technical evaluation by American intelligence teams documenting Japanese reverse engineering capabilities. But the strategic questions the Corsair represented had been answered conclusively through 4 years of combat operations. American industrial capacity could produce weapons faster than enemies could destroy them. American training programs could replace losses faster than combat could inflict them. American resources could sustain global operations indefinitely, while enemies struggled to maintain basic defensive capabilities. The Corsair continued serving long after World War II ended, French naval aviation operated the fighter extensively during the First Indochina War in the 1950s. During the Korean War, Corsairs flew ground attack missions supporting United Nations forces, demonstrating continued effectiveness despite the advent of jet fighters. Several smaller nations purchased Corsairs for their air forces throughout the 1950s, with some remaining in service through the early 1960s. The basic airframe design proved so successful that production continued until 1952, giving the Corsair the longest production run of any American piston-engine fighter. More than 70 years after the war's end, numerous Corsairs survive in museums and private collections worldwide. Several remain airworthy, appearing regularly at air shows where crowds gather to hear the distinctive whistling sound that once terrified Japanese forces throughout the Pacific. That sound, created by wind rushing through wing root intakes during high-speed flight, remains instantly recognizable to aviation enthusiasts and veterans who remember when it signaled the approach of overwhelming American air power. The story of the captured Corsair represents more than a tale of one aircraft or one battle or one campaign. It illustrates the fundamental transformation of warfare during the 20th century, from contests of individual skill and courage to industrial struggles, where material capacity determined outcomes, regardless of tactical brilliance or personal valor. Japanese pilots who faced Corsairs in combat possessed exceptional training, extensive combat experience, and remarkable courage. They flew aircraft designed by talented engineers who understood aerodynamics and pursued performance advantages through weight reduction and optimized designs. They fought with desperate determination against numerically superior opponents who controlled every material advantage. But individual excellence couldn't overcome systematic industrial inferiority. Japanese factories couldn't produce fighters as quickly as American factories despite mobilizing every available resource and operating under desperate wartime pressures. Japanese training programs couldn't produce pilots as quickly as American programs, despite accepting lower standards and abbreviated instruction. Japanese logistics couldn't sustain operations as effectively as American logistics, despite fighting close to home bases, while Americans operated across vast Pacific distances. The Corsair and its 11-to-1 kill ratio represented the visible manifestation of these deeper American advantages in industrial organization, resource allocation, and economic mobilization. The defensive features that allowed Corsairs to absorb battle damage and continue fighting reflected an industrial system that could afford armor, self-sealing tanks, and structural strength without sacrificing production numbers. The offensive firepower that gave Corsairs overwhelming advantages in combat reflected manufacturing capacity that could produce 650 caliber machine guns with thousands of rounds of ammunition for every fighter without straining supply chains. The performance characteristics that allowed Corsairs to dictate engagement terms reflected engine development programs supported by sophisticated metallurgy and precision manufacturing that Japanese industry couldn't match. Every statistic, every technical specification, every combat result reinforced the same inescapable conclusion that Commander Genda recognized standing beside the captured Corsair at Kasumigaura. You cannot defeat an enemy who builds fighters faster than you can shoot them down. You cannot win battles against opponents who train pilots faster than you can kill them. You cannot sustain operations against adversaries who deliver bombs in greater tonnage than your entire nation's industrial output across all sectors combined. The Whistling Death earned its nickname through the acoustic signature created by wind through wing intakes during high-speed flight. But the true source of terror lay not in the sound itself, but in what that sound represented. It announced the arrival of American industrial power made manifest in aluminum, steel, and Pratt and Whitney horsepower. It signaled tactical advantages that Japanese pilots couldn't counter through skill or courage. It confirmed strategic realities that no amount of desperate resistance could alter. Japanese forces who heard that distinctive whistle over Guadalcanal, Rabaul, Okinawa, and eventually Japan's home islands understood what it meant. Death arrived on inverted gull wings, delivered by 650 caliber machine guns firing from aircraft that Japanese fighters couldn't catch, couldn't outclimb, and couldn't defeat in numbers sufficient to matter strategically. The captured Corsair, sitting in a Japanese hangar, provided technical intelligence that confirmed what combat experience had already taught. American aviation had achieved air superiority through industrial capacity that Japan couldn't match, flying aircraft that represented the peak of wartime fighter development, piloted by adequately trained aviators, whose losses could be replaced indefinitely from seemingly inexhaustible reserves. The mathematics were brutal and undeniable. 12,571 Corsairs built versus 20,000. Japanese fighters of all types total. 11-to-1 kill ratios, sustained over 2 years of combat operations. 2,140 Japanese aircraft destroyed by Corsair pilots at the cost of 189 Corsairs lost in air combat. Thousands of American pilots trained annually versus hundreds of Japanese pilots. Unlimited fuel, ammunition, and replacement aircraft versus desperate shortages of everything needed to sustain military operations. These numbers told a story that individual heroism and tactical skill couldn't overcome. They explained why Japan lost the Pacific War despite possessing skilled pilots, capable aircraft, and absolute determination to defend their homeland. They demonstrated why the Corsair became the most feared American fighter among Japanese forces, who understood that hearing the whistling death meant facing an opponent who controlled every advantage that mattered in industrial warfare. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.